This last example is a little bit different from the other problems that we've looked at, but it covers a lot of the same ideas, and I think it's a really cool problem. So here we're going to be given the graph of f prime of x. I want to use this to sketch a possible graph of f of x. So we have the graph of the derivative over here. I'm going to see, hey, what information can I get from this graph to construct a possible graph of the original function f of x over here? So if you think about all of the examples that we've looked at so far today, almost every single one of them has started exactly the same. We've always said, oh, well, let's go find our critical numbers. Let's find places where the derivative is either 0 or undefined. So that's exactly the same way we're going to start this example. I'm going to look for places where my derivative is either 0 or undefined. If my derivative is 0, that means my derivative is going to be crossing the x-axis, because if we think about, again, this is the graph of the derivative of f prime. If I look at just this section over here, right here, my derivative has a negative y value. Here, on this just little section that I've circled, my derivative has a positive y value. But if I talk about this point right here, my derivative has a y value of 0. So I'm going to see if I can identify any places where my derivative has a y value of 0. I see one right there that I've circled. I also see one right here. And that's really it. There are no other x-intercepts on the graph of f prime of x. And here for this graph, it may be difficult to see, but we're going to say that the graph of the derivative exists everywhere. So we don't need to worry about cases where the derivative does not exist. So I need to construct a number line. I'm actually going to try and emulate the problems that we've looked at up until this point. So we said, okay, what are our critical numbers? What x values are these occurring at? So we've got this point right here, which looks like it's -3. And then this point right here looks like we've got an x value of +2. So, okay, we've identified our critical points. The other thing I would like to talk about is the behavior of our derivative at each one of these. For f prime, at -3, we said this was an x-intercept. It's crossing the x-axis right here. Same thing right here. It's touching the x-axis right there, which means that the derivative has a value of 0 at each of those 2 points. And that actually tells me a lot. That tells me that I have that horizontal tangent line. That's why I care so much about the value of the derivative there. The way that the derivative behaves if the derivative does not exist is a whole lot different than the way that a derivative behaves if the derivative is 0. So next, I'm going to look at each interval, just like we've done every other time. I'm going to look at to the left of -3, only this time I don't have an algebraic equation. I just kind of have to look over here. I have to think about, okay, on the left-hand side of -3, I'm talking about these x values, corresponds to this part of my graph. What's the value of the derivative over there? Is it positive or is it negative? Another way I can ask that question, is it above the x-axis or below the x-axis? Well, all of these values over here are below the x-axis. If it's below the x-axis, the derivative must have a negative value. So my derivative is negative. That tells me that my original function is decreasing on that interval. So okay, we've got that. What's happening next? Well, between -3 and +2, so on this little section, these particular x values, what's my derivative doing? Well, my derivative is above the x-axis. Here's that section of my derivative. Are those y values, are those positive or are those negative? Is it above the x-axis or is it below the x-axis? Those are all positive, right? This section that I'm highlighting right now, this is all above the x-axis. That's positive. So my derivative has a positive value, means that my function must be increasing. So okay, we've gotten the behavior at the first 2 intervals. The last one, I need to look to the right of positive 2, so I'm talking about to the right of positive 2, this area over here. What's my function doing? Well, my function is above the x-axis once again, right? All of these y values that I'm highlighting right now, those are all positive. They're all above the x-axis. So my derivative has a positive sign, which means that my function is increasing on that interval. So what's going on at each one of these points? Well, at -3, again, sketch that in if you need to. At -3, we're decreasing and then increasing. I think if you sketch that in, it's a lot easier to see, oh, this right here at -3, we've got a local minimum. That I know, because we're decreasing and then increasing. We've got that horizontal tangent line right there. 2, on the other hand, is a different story. This one's a little bit tricky. I've got a horizontal tangent line at 0, or excuse me, at 2. But look at the behavior on either side. On the left-hand side, it's going to be increasing. And then it kind of levels out here so that I get that horizontal tangent line. And then after that, it continues to increase. We saw an example like this earlier. We saw an example, I believe it was the second problem that we looked at in this section. So here, we're not going to have either a max or a min. And if you go back and look at your first derivative test at 2, we have neither a local max nor a local min value. Or you could just say it's not a local extreme value. So I have a lot of information about my graph just by looking at this number line that I've constructed right here. This is a really good start to my problem. Now I just need to kind of interpret it and use it to help me construct a possible graph of f of x. And I keep throwing this word in there nonchalantly. I said possible graph. And that word's actually really important because there's really no way for us to know what the exact graph of f of x is just with the information that we have. It's impossible. We can't do it. But we can get a possible graph of f of x. We can sort of describe the general behavior of the function at these particular x values. So what I'm going to do is I'm going to plot a point at x equals -3, and I know that that's a local minimum. And where you place that point, I don't think it really matters. I'm going to place that point, how about right here? Because I know at that point I'm going to have a local minimum. So that looks like my function is decreasing. And again, if you need to, maybe we sketch in that horizontal tangent line. I do think that's helpful. Our function is decreasing on the left-hand side, has the horizontal tangent line right there at -3. And then after that, it's increasing again. Now, I could have placed that point at a different y value. I could have placed it, say, up here, where I have this horizontal tangent line. It's decreasing on the left-hand side, levels out to achieve that horizontal tangent line, and then it's increasing after that. And both are perfectly fine. It doesn't really matter what y value you place it at. What matters is the x value that it occurs at. We said that we have that local minimum at x equals -3. That's the important part. So where you place that doesn't really matter. It doesn't even have to be at a whole number. I could place it, say, right here and say, okay, well, I've got a horizontal tangent line. My function is decreasing. It levels out just for a moment, and then after that it's increasing. It looks something like this. And I'm not really happy with that. I'm going to fix that up a little bit. There we go. That's a little bit better. What about at 2? So here's something different happening, and let me erase this just so that I can start fresh. It's decreasing and then increasing. At 2, we have some sort of odd behavior. We said, okay, we have a horizontal tangent at 2, so okay, what's going to happen there? It's going to, let's do this. Cannot get my graph right. There we go. So what's going to happen? Well, it's going to be increasing until I get to 2. So right here at this x value, and again, it doesn't matter what y value it occurs at. Once I get to that x value, I should have a horizontal tangent line. So So my tangent line should be horizontal. But the behavior is going to be slightly different. So my graph sort of needs to, almost in a way, level out. So let me draw in what that might look like here. Once I get to 2, my graph is sort of going to level out, and that's even a little bit drastic for what I want to do. My graph is going to level out just for a second, and hopefully we see that horizontal tangent line right there. But instead of going back down like we would expect to see with a local maximum, this time it just says, you know what? This function continues to increase on the right-hand side. So after that, it just continues to increase. So at that point, we have neither a local maximum nor a local minimum. We just have this kind of weird turning point in our graph. And we'll talk way more about those points in the next section. Don't you worry, we'll get there. But the important part is we don't have a maximum or a minimum at this point. But we do have instead that horizontal tangent line. That's the behavior I think that's really important for this graph. So I think that these problems are really great to practice. Usually I think graphing the local min and local max values, those are a little bit easier for us to manage. It's graphing these points that are neither local minimum nor local maximum values. These are a little bit trickier. And so I would encourage you to get some practice in with those. I also think that this is an excellent problem to study if you were, say, preparing for a quiz or an exam. I don't know. I'm just thinking out loud. I'm just a math teacher. What do I know? But go ahead and take a look at problems like these. I think that this is a super good problem to study. And I will see you in section 4.2.